So, what actually happens when two entire universes try to occupy the exact same space? Right? In traditional physics, you'd probably imagine this catastrophic collision, just a total breakdown of reality, or maybe a mathematical paradox that just completely destroys both systems. It is literally the ultimate sci-fi high-stakes scenario. But what if there was an underlying structural framework? Like a cosmic set of traffic laws that actually prevents these apocalyptic multiversal crashes. Well, welcome to this explainer, where we're going to unpack exactly how that might work.
Today, we're looking at a genuinely fascinating working paper from August 2026 by Dr. Melvin Sewell over at the Cosmic University of Echo Rift Studies. His paper introduces this mind-bending mathematical framework known as Structured Multiversal Interactions, or SMI for short. I kind of like to think of this as the definitive rulebook, really the ultimate set of cosmic traffic laws that are specifically designed to govern what happens when multiple multiversal domains interact, merge, or overlap.
Okay, let's dive into this. Dr. Sewell formally defines SMI as a closed, singularity-free algebraic system designed specifically to prevent boundary failures across multiversal domains. Okay, that's a mouthful. In simpler terms, it's a mathematical safety net. Think about it. When computing complex relational mechanics between totally different universes, the equations can really easily break down into impossible scenarios, like a division by zero crash, but on a massive cosmic scale. SMI is the algebraic architecture that basically ensures reality's software doesn't crash when two universes touch. And this brilliantly illustrates how it solves a massive theoretical problem. On one hand, standard boundary failures give you those division by zero collisions, infinite recursive loops that just grow completely out of control, and chaotic information dissipation. Basically, absolute destructive chaos. But on the other hand, SMI steps in to provide closed algebraic systems and exact information conservation. So the framework ensures that instead of just annihilating each other, overlapping universes can mathematically resolve their boundaries gracefully.
To really grasp how Dr. Sewell pulls this off, we're going to break this explainer down into 4 logical steps. First, we'll look at the multiverse collision problem, then the 5 axioms of interaction, followed by the holographic horizon, and finally, proving it with Python.
So, let's kick things off with Section 1, the multiverse collision problem. We really need to establish the foundational rules of the road for universes that are trying to merge. I mean, when domains get infinitely close, how do they keep their distinct identities? So, the crucial point is found in axiom I, which Dr. Sewell calls superposition invariance. If two distinct universes reach 100% structural identity, meaning their physical distance is effectively zero, standard math says they either fuse completely or just error out. But axiom I introduces a sovereignty scalar. It's basically a mathematical ID badge that never equals zero. This is what allows two universes to coexist in the exact same physical space without merging together. They get to share the same space while remaining mathematically sovereign. Which brings us right to axiom 2, perfectly summarized by this quote straight from the paper. Impedance-bounded null contact. Imagine an active, thriving universe bumping up against a null domain, literally a zero-entropy void. Without some kind of protection, all the information and energy from that active universe would just instantly drain right into the void. Dr. Sewell establishes a finite boundary impedance parameter. Think of it kind of like electrical resistance, but for reality itself. It acts as a vacuum resistance that tightly regulates the maximum flow of information, keeping the active universe from bleeding out its existence into nothingness.
Let's move to Section 2, the 5 axioms of interaction, and see how this builds.
So, we've established how universes avoid crashing into each other or draining into the void, right? Well, now we need to look at how these multiverses actually observe each other. Axiom 3 guarantees 100% signal fidelity. You see, when universe A looks at universe B, and B looks back at A, you run a huge risk of an infinite feedback loop of observation that builds toward infinite energy. Dr. Sewell solves this mathematically by locking the data transfer into a stable standing wave. It's kind of like a perfectly balanced echo chamber. The data bounces back and forth flawlessly without spiraling totally out of control.
But what happens when one universe actually tries to absorb information from another one? Axiom I deals with polynomial intake satiation. Let me translate that into plain English. Even though a universe's overall spatial capacity might be able to expand infinitely, its instantaneous ability to take in new data has a mathematical hard stop. There are internal polynomial capacity functions acting as a strict speed limit for cross-domain information absorption. So yeah, you can download the data from another universe, but only at a carefully regulated bandwidth.
All right, moving on to section 3, the holographic horizon.
If information is constantly moving between domains of totally different sizes and dimensions, where does all the excess data go? Dr. Sewell proposes that the boundary actually acts like an infinite cosmic hard drive. Let's translate some of this dense matrix calculus, shall we? First, the global domain conservation metric ensures the total multiversal information is constantly tracked and preserved. Next, the dimensional projection operator prevents data loss during downmapping, like when a higher dimensional universe projects down into a lower dimensional one. And finally, the state retrieval operator perfectly reconstructs the original state using inverse operators. The plain text outcome here is absolutely profound. Across the entire multiverse, information is never, ever lost.
Now, what's really interesting about this slide is how that preservation actually happens physically. When you project a complex, high-dimensional reality into a simpler, lower-dimensional space, you're obviously going to have leftover data. Dr. Sewell defines this leftover data as excess degrees of freedom. But rather than being destroyed, these high-dimensional structural states are non-destructively encoded directly onto the universal boundary horizon. They just exist purely as surface entropy density. Essentially, the higher dimensional reality is seamlessly backed up on the two-dimensional surface enclosing our universe. Pretty wild, right?
And that brings us to our final section, number 4, proving it with Python.
Now, you might be sitting there thinking this all sounds like highly theoretical, unprovable science fiction. I get it. But what makes this framework so incredibly unique is that Dr. Sewell actually grounds these theories in code, using pure standard library Python. No fancy external physics engines, no complex libraries required. His script sets up helper matrix operators. It performs matrix transposition, moves right through matrix multiplication, and uses matrix trace functions to calculate the exact state of the universe both before and after a lower dimensional projection. Just by running these standard steps, the script programmatically verifies the exact holographic boundary storage equations we were just talking about.
And the result of that code? A margin of error of less than 10 to the power of -6. Literally less than 1 in a million. When the Python script runs the state retrieval operator to try and reconstruct the original high-dimensional state from that boundary data, it checks the difference between the original information and the newly reconstructed information. That margin of error is virtually 0. These numerical checks confirm exact information conservation and reversible state mapping with almost absolute precision. The math checks out, the boundary is closed.
So let's take a step back from all the matrix calculus and the Python code for a second and really think about what this means for us. If Dr. Sewell's framework is correct and the universal boundary horizon perfectly stores excess degrees of freedom from higher dimensions, it begs a pretty incredible question. What information from a higher, way more complex reality is invisibly encoded all around us right now, just resting quietly on the holographic horizon of our own universe? It kind of leaves you wondering if our day-to-day reality is just a lower dimensional projection of something so much larger. Anyway, thank you so much for joining me for this explainer, and keep questioning the boundaries of your reality.